Hey Phys kids, it's Campbell here. In our last Gauss's law video, we're going to look at plates. So when we have a conducting plate that's big plate, infinitely large, the field strength is going to be the same. Because remember that in conductors, the charge is going to spread out. So I have a uniform charge density, and so I'm going to have a uniform electric field pointing up and pointing down if this is a positive plate. And so once again, we're going to use a cylinder. We're going to use a soup can shape, or maybe we'll call this one a tuna can. But the electric field this time isn't going to be coming out of the rounded sides. It's going to be coming out of the ends of the can. For a plate, we're going to have to use the surface charge density sigma, which is the charge per unit area. And so when I write my Gauss's law, right, the surface integral of E dot dA is equal to Q enclosed over E naught. My Q enclosed is going to be the amount of charge that's enclosed in the area of my soup can. So that would be sigma times the enclosed area. And remember that this area is the area of my imaginary Gaussian surface. And if I look here, though, I have two places where the area vector is sticking out of. So I really have two electric field vectors per area here, or for each area. And I'm just going to call that area A. I'm not going to break it down into fancy 2 pi r sort of stuff that we had to do when we were doing that disk of charge and we were adding up all the little r's, because it's just the same as what? That one. So that's going to equal sigma, the area enclosed, which is the same as that area, over E naught. And so I get that the electric field for a single plate of charge is equal to the surface charge density over 2 E naught. Well, that seems kind of simple, right? What if we, though, have two parallel plates, right? Usually you don't just have like a single plate of charge, you have two parallel plates. Well, if we have two parallel plates, then the electric field inside is a sum of the two electric fields from the two plates. So like if I had a plate here and I had a plate here, right, I would have, and this would be the negative, so the electric field would be pointing in here and pointing in here, and pointing out here and pointing out here. And so we would have two electric field vectors, each of the single plate magnitude. And so here would be like plate 1. Maybe that's my positive plate. Here is my negative plate. Remember, we don't use the sign of the charge when we do electric field because it's about direction. And notice the direction is pointing this way, all in the same direction towards the negative plate, away from the positive plate. And so, right, we're going to get rid of that because it's going to be 2 sigma over 2 E naught, which gets us to the electric field being this. Now, if you look at the fact that sigma, right, is the total charge on the plates divided by the area, I can get rid of sigma and I can put in the QA thing. And I get that the electric field is Q divided by E naught A, which is an equation for the electric field of parallel plates, which may or may not be on your equation sheet. I'm not sure. We'll have to check that out. So let's check that out in class. If you have any questions, ask me in class.